Give me a moment to share my screen. Okay, so let me just check if you can see my slides. All right. So one moment so that I can actually see you while I'm talking as well. Excellent. Okay, thanks.
So a little bit small, Mario. It's taking just like a small piece of our screen.
Is it full screen now?
There you go. Thanks.
Okay, good. Thanks, Colin. Thanks, Meg. I will warn you that BlueJeans tends to take down my computer, so if I disappear for a second, just wait for a minute. I'll reboot. But I hope it's not going to happen this time. I'm Mario Jurić. I lead the Rubin Solar System Pipelines construction team. I'll give you a quick solar system overview of LSST data products and also an update on where we are with the development. One thing to point out is these days I tend to write PowerPoints. The folks who are really the heroes in the background are research scientists and postdocs, and this really large band of undergraduates and graduates that we've gotten interested in this project and who are now contributing to the pipelines. Okay, so one slide about Vera Rubin Observatory. It's an 8.4 optical survey telescope in Cerro, Chile that's currently being constructed. It's going to have a huge 3.2 gigapixel camera, 2-second readout. We'll be able to scan essentially the entire sky once every 3 days. Site construction began in 2015, so almost 6 years ago, and the 10-year LSST survey should be starting in October 2023. You've probably seen these photos already, but I always find them pleasing to look at again, especially after working on this project for more than a decade now. It's real. It's there. This is a screen cap from a video of the top end of the telescope being mounted. So you can see this huge piece. This, I've been told, is the largest crane in the country of Chile that was brought to the summit for this reason. So the telescope is there. It's getting ready to. The construction is being finished and it's getting ready to start observing in about a year and a half or so. For science themes, dark matter, Milky Way, exploring the transient optical sky, and the one that we care about here, an inventory of the solar system. The way to think about LSST, again, if you're new to the project, is this is going to be a single uniform survey of the visible sky. The way I like to think about it is, imagine you have a telescope that makes 500 pointings per night, 500 unique pointings per night in the sky, 2 visits to each pointing. With each visit, you get 10 square degrees of area covered down to 24th magnitude in the R band. So that gives you about 5,000 unique square degrees surveyed per night, and we repeat that for 10 years, or about 3,300 nights. So all these data are going to be collected. They're going to be processed automatically and generating data products. So none of us are going to be working with the raw data, at least initially. There's going to be no point in working directly with the raw data, but what we're going to be doing is we're going to be taking catalogs, taking cutouts, and taking alerts from the observatory to do our science. So let me talk for just a brief few minutes about what data products you can expect. And again, as Meg mentioned, none of this has changed since for the last, I think, 2.5, maybe 3 years. So if you want an expanded introduction to this, take a look at my talk from last year or from DPS from this year. But just a quick summary here to set the stage for everything else. We're going to have 3 types of data products. One, we're going to have real-time alerts within 60 seconds. So this table gives you an idea of what we're going to get. This is mostly for objects that are either known. So as the telescope observes, it's going to do image differencing. It's going to perform image differencing within about a minute of each observation. It's going to find objects on the differenced image. And if that object was a known moving object, it's going to tag it with its designation. So that means within about 60 seconds, you'll get an alert to, asteroid so-and-so or comet or cloud object so-and-so being at this position in the sky having this brightness. What is that useful for? It's useful for things like looking for outbursts because we'll know what the predicted magnitudes are going to be. We'll know whether this object is DSF-like or not, and you'll be able within 60 seconds to know whether something seems odd with a known object. The other thing that's going to be coming out of these real-time alerts is we're going to be measuring whether objects are trailed. So if there's a trailed moving source that's been detected, that will be a fairly simple query to do on the alert stream. So within 60 seconds, we'll have an idea of everything that's moving and be able to react to that as well. So these are the real-time alerts and the two main use cases for them. Where I think most of the science is going to come from is the daily catalog. So on a daily basis, what we're going to do is we're going to be collecting all the data that the telescope has collected over a period of about 2 weeks. We're going to be analyzing it in chunks of about 2 weeks for any sources that are consistent with asteroids or with objects moving through the solar system. So we're going to be constructing tracklets. We're going to be linking tracklets across days. The strategy that was originally conceived for the Pan-STARRS survey, that's what LSST is going to be executing. We're going to be reporting any discoveries to the Minor Planet Center. And then on a daily basis, we'll be computing a daily catalog of objects that LSST has seen and discovered. So this catalog is going to include orbits. These will be computed by the Minor Planet Center, just so that we don't have different solutions depending on which database you look at. But what's going to be in the LSST database are things like light curve characterization, absolute magnitude estimates, so H and Gs for each individual band, some convenience things like computing the MOID, like MOID computed, and the various extended S indicators. So whether these objects are, whether any given object is consistent with being a point source or perhaps being a comet. I suspect that this is going to be the way most of us interact with this data set, at least in the first couple of years. And then finally, once a year, we'll be producing high-quality data release catalogs. So there'll be two kinds of these data release catalogs. One is going to be essentially just like the daily catalog, but with a higher fidelity reprocessing. In a year, we will have accumulated lots of knowledge about the telescope, about how to calibrate it, about where were the bugs in the software. So all the things that were potentially had quality issues when they were done in real time, we'll be able to do that very carefully. And for data release, produce one gold version of the daily catalog that you can then use for papers, for things that are not urgent, that don't require a reaction on a daily basis. The other catalog that's going to be produced is the LSST catalog of solar system objects. So the daily catalogs include everything, including objects discovered by other surveys. So we'll be looking for them in the LSST and finding their flight curves and publishing the LSST data about them. This other catalog will be just objects seen in the LSST and by the LSST. So it'll be much more suitable for population studies because we'll know the selection function for this catalog very, very well. This is still far away from us, relative to the start of the survey. So the first release is going to be about a year in. So most of what we're focused on right now is getting these daily catalogs done. And we'll start talking about these data release catalogs a little bit closer to the beginning of the survey. So those are the data products. As I said, nothing's changed over the last 3 years. If you want an expanded view of that, take a look at the documentation we put out. Development updates. So we're busy writing pipelines. Meg already talked about the hardware, and we're waiting for COVID impacts to relax so the hardware can get built, but we're making sure that we have the pipelines ready when the hardware is on the summit so we can start working on it, processing the data immediately. Couple of highlights about the software. So linking is Siegfried Egel has been writing algorithms, writing pipelines for tracklet linking. He has a code called HelioLink 3D, which is an extension of Matt Holman's HelioLink algorithm. Ran the prototype in February on a linking of objects that we expect to find with LSST, passed with flying colors, and Siegfried is preparing a paper explaining exactly how it works and what the differences are. One thing to announce and note here is Siegfried's leaving for a faculty position at UIUC this September. So first of all, congratulations to him, and thank you, Siegfried, for the last 3 years and all the awesome work you've done in LSST. We'll definitely keep Siegfried in our orbit, pardon the pun, and continue collaborating, and he'll be helping us with the pipelines over the next year or so. But we are getting a very, very highly qualified replacement. Ari Hanze is coming to us from Atlas from Hawaii in September. So now I think we're going to be getting another person who's been in the trenches, discovering NEOs, discovering asteroids, and doing all kinds of other ancillary science. So with Atlas, and we're very much looking forward to that as well. So overall, I think this is all good news. Faculty position, new person, and healing that's working. Moving on, we have implemented trail source fits, or at least the first version of trail source fits. So I mentioned that LSST is going to be discovering objects that trail on images, and we're going to measure them. We're going to measure them in real time. So one of our undergraduates, actually, Zach Langford, implemented trail source fitting algorithms for the stack. There are 2 algorithms that he has right now, estimation from adaptive second-order moments, which is something that most dark energy-oriented surveys have, and then the Verish et al. Algorithm that's effectively simplified forward modeling. And one curious thing about this is that we're finding that second-order moments are about as precise as Peter's algorithm at a fraction of the computational cost, because we already have them. So we're writing that up. It's great news because it means this won't add much computational, in terms of computational load to the solar system pipelines, which we have to the real-time pipelines, which have to complete in about 60 seconds. So this is now in the stack. If you want to go see the code, it's here in Mesh Extensions Trail Sources, and there's a whole bunch of branches with new improvements that Zach is putting in on a daily basis. So this is really good. We haven't had any of this last year when I gave an update, so this is all new. Another thing that's new relative to last year's sprint, some of you have already seen and heard this. We've done a first data exchange test with the Minor Planet Center back in October 2020. So we made mock full-size submissions for the first 3 weeks of LSST data, submitted it to the Minor Planet Center, and then the staff there took them over, accepted, and then manually processed the submissions, just because the automated systems are not set up yet to take simulated data in bulk. So there had to be some care so that you don't discover, so that you don't find in real NPCR, you don't find our simulated data. So we ran this process, and for a typical LSST night, the process took about 4 hours, which is great because that's our computational budget. There's still some steps to add there, but bottom line, I think based on this, we've identified no architectural bottlenecks, so no something where we have to invent new technologies, where we have to come up with completely novel ways of doing things. Assuming MPC capacity is enlarged as expected, and capacity here means computational capacity, we don't expect significant problems. But of course, we'll be doing this on an annual basis, so we're planning out the next one for September, just to make sure that we have everything ready in time. One interesting detail about this, we've discovered, we've kind of known, but this really brought it to the fore, pact designation, MPC pact designations. There are only about 16,000 pact designations available for any 2-week period. We blow through that in a night. So we'll have to come up with a new way, potentially, to transmit designations in things like NPCR, whether it's even more complicated packing scheme or just completely abandoning them. It's TBD, but it was kind of interesting and satisfying to see how many objects we're likely to discover, and the nice problems we're having because of that. And that brings me to kind of the last slide here in the updates is, I mentioned here we've had simulations that we built last year, and we used at the sprint last year, which were quite rudimentary, but they got us through the first data exchange challenge. Now we have a new release of simulations. Last year we simulated on the catalog level, so not in the image level. We've simulated a 1 year's worth of data. This year we have a full 10-year data set, so that's over 1 billion measurements. We've simulated all solar system tables. So in the database we have the solar system source, we have the simulated NPC orb, and the input data that actually went into the simulation. This is the Gravital S3M model, which we're still using. And we have the solar system object table. So this is the table that has things like absolute magnitude and slope parameter fits. And this is another thing that was developed by by the group this year. This table is generated by a prototype, by the first release basically the daily data products pipeline. So this is the pipeline that's going to be generating that data product, that catalog. So what you're seeing here is what you'll be seeing here is data as the pipelines are generating them. We'll also use new cadence, so baseline 1.6 to build this data set. We now have realistic magnitude and astrometry errors in it as well. As I mentioned, we have absolute magnitude fits, and all of this is now in the same technology that's been chosen to run the actual database, Postgres SQL. Originally, this daily database was supposed to be in MariaDB. The database team switched to Postgres last year, and so now we've done that as well. One of the things I want to emphasize here is that this has really been community developed, including very, very strong support from the Solar System Science Collaboration. So some of the folks I really want to give a shout out to are Shantanu Naidu from JPL, who's built the simulator that we use to find whether objects are in field or not. Grigory Fedorovich, who's done a lot of work on adding the post-processing steps to that simulator. And then Rubin's SSO team and UW's Solar System Group's most excellent band of undergraduate, as they call them here, who have been implementing all these various measurements and columns that we have in the simulations, and hopefully learning something about LSST and the solar system now. So if their application comes across your desk for graduate school, hire them. They know how to work with LSST data. Okay, so we have these simulations, and for the remainder of my time, I just want to walk you through them in Jupyter Hub. We have a Jupyter Hub setup for the sprint. It's the same one as last year. To have access, you need to be in the Solar System Science Collaboration GitHub organization. If you're not, please let us know. Best way to do it is on Science Platform channel on the SSC Sprint Slack. But if you do have if you are a part of it, and if you used this last year, you are, then go to sssc.dirac.institute, and you'll be greeted with a Jupyter Hub there that I'll walk you through. So here, I'm already logged in. Let me log out just to show you what it looks like. So if you go to sssc.dirac.institute, this is what you'll find. Click on Sign In with GitHub. If this is the first time you're signing in, you'll get a couple of screens asking you to confirm things. Second time, you're going to just log in, and you get all the files. If this is the first time you're logging in, it may take about 2 or 3 minutes for everything to spin up for you to get to this stage. So please be patient until the cloud gives you your computer for the day. All right. So one thing that I want to show you are these. There's a demo notebook that we put together for the simulation. The simulation is in the LSST SSSC GitHub organization under LSST simulation repository, and I'm going to walk through that in here in Jupyter Hub. For you, you can go and clone this yourself and then walk through it as well. So if you hit New Terminal, you can simply go and run something like git clone, and then paste the link, and that'll bring it over to your account on Jupyter Hub. And if someone can actually copy and paste this to Slack to make it easier for folks to follow, I'd very much appreciate it. I'm not going to do this because I already done it, and I have it in my workspace. So here is that cloned LSST simulation repository. I'm going to go click on Notebook, and then open this notebook and then show you a little bit about what's in there. Let me restart the kernel just to be on the same footing like everyone else. Okay, so this is a notebook that just runs a couple of representative queries against the database and shows you what's in it. The hope here is that this is a good starting point for you to figure out what's in the database and then start playing with it yourself. I'll make this a bit larger, so I hope you can see it. Colin, can you do a quick nod if you can read what's in the notebook? Perfect. All right. So some initialization, connecting to the database. This here is how this file on Jupyter Hub is where we have the password for the database. So we can quickly rotate it if needed. But if you're writing your own notebooks, I'd recommend you do something like this, or use a stanza that looks kind of like this. The tables that are currently in here, there is soul system objects, sources, MPC orb, and data sources. And again, MPC orb here is the mock MPC orb. This is really S3M model. How many rows does each table have? So if you run this query, I won't run it right now because it takes about a minute to run. It will give you a list of rows in every table, and you can tell there's about 10 million soul system objects. So these are objects that LSST has observed. There's about 1 billion of observations. That's the SS sources and DS sources tables, and the input catalog was 14 million objects large. So to give you a feel for what the tables look like, let's just grab 5 random rows from each of them. So here's DS sources. So DS sources are sources that are detected on different images with LSST. Their IDs. There are the time observation, RA deck, observational errors. These are in degrees. That's why it seems so small. And similar to noise, magnitudes, sigma, and filters. There's the SS source table, which is a one-to-one map with the DS source table that brings in things like ecliptic longitude and latitude, heliocentric distances, topocentric distances, various kinds of things that we care about for solar system. The SS object table summarizes those observations. So basically, gives you the arc, for example, total number of observations. MOIDs have not been computed yet. I apologize for that. Didn't realize that until this morning, actually, when we loaded everything in the database. But we'll fix that in the next couple of days. And then the fits for magnitudes or for slopes and absolute magnitudes in each of the 6 bands. So, for example, this here is the Y band, G12, the error on that fit, covariances, chi-squared, etc. And then the input population is in the MPC orb table. So designation here are the mock objects, mock object names from S3M. But these few entries give you a sense for what's in the database, and you can go and play with it. So let me show you the results of playing with it. So here's a quick query to just grab one visit. It returns really fast. It's done in milliseconds. And here's a visit. You can see the nice LSST footprint. There we take chip gaps into account, all of that. So it's all in here. Now I can grab the same data in ecliptic coordinates. Interestingly enough, this takes about 30 seconds as opposed to milliseconds up here, just because of the way database works and are not entirely super intelligent when figuring out how to grab data and do joins. So let's wait for a second there for this to come back. Should be no more than about 30 seconds, up to a minute, actually, depending on how many of us are hitting the database at the same time. All right, and then when you run that, you can also make a plot. Here's the same plot in ecliptic coordinates. Next thing you can do is you can go ahead and ask for a whole night of observations. So here I have, give me everything between MJD 60,000 and 60,000 minus a half and 60,000 plus a half. And here's a plot of what's come back. I can repeat the same thing for the full month of the survey. It's exactly the same query. It's just that I took, now I asked for the first night of the survey and then first night plus 30 days. Here's what a night worth of LSST or a month worth of LSST data are going to look like. Next, I have an example of how to get a phase curve for a single object. So let me stop this running query just because I think everyone's running this notebook at the same time, so it's taking a little bit longer. But I do want to show you the phase curve query. So if we run this the query to get the phase curve, this usually takes on order of also less than a minute or so. What comes back are all the observations. Here are the observations that I've overplotted, that are simply plotted as phase angle versus distance. And then I can grab the age and G fit from the object table and then overplot that. Thank you, whoever implemented this in SBPy. That's what we're using. It's been tremendously useful. And here's what the fit looks like. And this is a fit based on 10 years of observations. The final thing that I have in this notebook is a look at the population. So what we have here is just a quick query to bin what's in the NPC orb table and to plot age magnitudes. And what you get is essentially very similar to what you see in the Gravid Owl paper, including the warts where there's some bounding in different bins depending on how, or given how the sample is constructed. So between all these queries, I hope it gives you an idea of what's in the database and how to use it. One caveat is that this is the first time we are deploying this, and the first time that maybe 30 people are going to be hitting this database at the same time. So expect that it's going to be a bit slower than the timings you might see in this notebook. I've tried to run a couple of things. Some things ran fast, some things ran slower than when I was there when I was on the system on my own. That's going to get better when this is deployed in production. But yeah, keep that in mind. Another thing I'd like you to think about here is feedback. So if you find some of these queries cumbersome to write, difficult to understand, then let us know about it. Now's the time to do that because we can still make changes in time for the real thing. But that's it. Let me stop here. I think I have maybe 2 more minutes left for questions, and we can definitely talk about this throughout the week. All right. Thanks, Colin.